Let's imagine for a moment that you and I make a bet, and you bet me $1 million that I can't prove to you the area of this crescent shape right here. And I say, you know what, I think I'm going to make that bet. I think I can prove that I can deductively demonstrate beyond a shadow of a doubt what the area of that crescent shape is. And in fact, I've kind of done this in math classes previous. I've actually taken the area of this big curve and found the area of this little curve right here and subtracted the area of this little curve down here, and what's left is the area of that crescent. And so I go, well, the way that we've done this in math class is we make a bunch of little rectangles because you really can't calculate the area of something that has a curve to it. So what we do is we make a bunch of rectangles. We find the equation of this curve, which is the way I have it drawn out. It goes from 0, it goes to 1, to negative 1, and which means that its radius is 1. And so the equation for this curve, for this semicircle, is the square root of 1 minus x squared, which then means that the equation for this little circle is negative 1 plus the square root of 2 minus x squared. And the reason being is because the radius for this little circle is the square root of 2. And so I could go along and make all these little rectangles by using this relation right here, which places my point for my f of x at the right corner, so I can go up to that right corner, go over a certain delta x right here, and I could multiply the width times the height, add all my rectangles together, get an area. And then I find that if I've got 12 of them, the area of my big circle is about 1.53 something. The area of my little circle is around 0.566 or something like that. So it looks like if I take 1.53 minus 0.56, I got around 1. And then if I have 24, this area becomes 1.55 and this area becomes 0.596. It's closer to 1. I take 300, got 1.57 minus 0.57. There's some digits on the back side of each. It's not really quite 1, but it's pretty darn close. And so I look at you and I go, hey, how's that? The area of this crescent is 1. I won. You say, not so fast. I wanted you to prove to me, beyond a shadow of a doubt, exactly what that area was. You didn't win your $1,000,000. And I say, yeah, but Seeker, look how close I am. I mean, I'm extremely close. Not good enough. We're talking about $1,000,000 here. And I say, okay, well, how about we do this? How about I take it to infinity? How about instead of n equals 300, I go all the way to infinity? If I go up here in my equation, this is the equation right here for the summation for the big circle. If I take it and I take n to infinity, that means this n goes to 0. This one does here too. But if this n goes to 0, this whole thing equals 0. Here I've got 1 plus this part right here, and if n goes to 0, I have negative 1 plus 0. So this one goes to 0, this one ends up being negative 1. And so if I take everything to infinity, I got 0 minus negative 1, which equals 1. I won. You say, no, not good enough. What do you mean? Seeker, you say to me, Mark, but you can't go to infinity. It's not possible. If I give you all the time in the world, if I give you eternity, there's still going to be one more rectangle you can add in. You're still going to be off by one more rectangle. You still haven't proven to me that it equals 1, even if you go to infinity, because you can't. Infinity never ends. Wow, seeker, you're right. The sum of these parts will never equal the whole. I cannot deductively prove to you by summing the parts, by looking at the parts, I cannot prove to you the reality of the whole. You're right. Maybe there's some other way though. I don't know. So I come back here and I look at this and I go, well, you're right, we can't prove it's one. But we do know that there's something called proportionality. And in fact, I asked you if, for example, the area of the circle was proportional to its diameter. And you agree. Proportionality exists. There's actually a mathematical theorem of proportionality. There's a law of proportionality. And I look at our figure again, and I notice, wow, you know, if I take this radius of 1 and I look at that as the thing that draws out my large circle, and I make a square out of it, I notice that this part along this chord, this part outside this chord, is outside 1/4 of that square. There's 4 of them. There's one over here, there's one over here. I could draw another one over here if I wanted to. I could draw another one over here if I wanted to. And then I find out, you know, if I really look at this, I go, wow, this square, let me see, the sides of this square is a square root of 2, right? See, that's 1, that's 1. That means the side of this square is a square root of 2. And if I want to know the area of this square, I multiply the square root of 2 by its square root of 2. Whoops. Which means that the area of this square is 2. Well, what's the area of this big square? I look at that and I go, wow. If this is 1, that means this length is 1 and this length is 1. That means the side of this square is 2. So if I square this, it's 2 times 2. It's 4. This square is twice the size of that square. Exactly. By proportionality. It doesn't matter what the individual lengths of the squares are. The law of proportionality, which you agreed to by saying that the diameter, the area of a circle is proportional to its diameter. You just agreed to it. That means that this square is half the size as this square. And I drew out an arc, and I could make 4 of these, which is 1/4 of the circle. And basically when I draw this arc here, I do the same thing. I could draw another one out here, I could draw another one out here, I could draw another one out here. So this is 1/4 of this bigger square. This square is twice the size of this smaller square, which means that this arc, which is 1/4 of this square, is twice the area of this little arc, which is 1/4 of this smaller square, which is half the area. Law of proportionality. What does that mean? That means that the area in this little arc right here is half the area of this arc right here. That means I can fit 2 of these little arcs into this one. And if I do that, let's say if I take this part right here, right, and I put it in here, and I take this part right here and I put it in here. Now what I have is that the area of this crescent shape is equal to the area of this triangle right here. And I can prove the area of that triangle. It's half the base times the height. What's the base? It's 2. What's the height? It's 1. 2 times 1 is 2. What's half of 2? 1. I've just proven without having to use any calculus. And I did it rectilinearly, and I did it so that the conclusion flows directly from the deductive premises. I've just proven it's 1, but I've done more than that. I've proven that this was valid. I've proven that even though I could not deductively, by doing it in a calculus way, prove that this was 1. Nonetheless, I've shown that it is 1, and I've shown that this was true. So what am I saying? I'm saying that there are things that exist in this universe that are not describable in terms of natural laws only, just as this sum of this crescent isn't describable in terms of the sums of these rectangles. If you consider this 1, this area of this rectangle, being analogous to free will, and you consider that these rectangles would be analogous to, say, natural laws, even though that the sum of this crescent is the result of summing the rectangles, it's still not reducible to not, to just that process. You say axiom of naturalism, all natural entities are subject to natural laws only. Okay. Premise 2, all decisions are natural entities. Well, when you say natural entity, what you really mean is a physical entity, right? A brain state, a motion of an atom, something physical. Free will, decisions, these things, although they are the result of physical processes, are not themselves physical entities. And so it's entirely possible to have something that's not a physical entity and be totally within the natural universe. Nothing supernatural about it. So how do you get to decisions and free will? How do you reconcile that? Well, the same way you reconcile the fact that this area is 1 by taking these rectangles to infinity. What do we mean when we say to infinity? We mean everything, all at once. Only then is the emergent property recognizable. And even though this emergent property is the sum of all these natural processes, never are the natural processes the phenomenon itself. So you can look at all the natural laws, all the brain states, all the physical things, and you will find that even though your free will and decisions and all that are born from those things are not the phenomenon itself. What is the phenomenon itself? It's the part where you get to everything all at once.